On this question, we want to determine the real solutions to the system of nonlinear equations. In this example, we have x squared plus y squared equals 16, y squared minus 2x equals 16. And so this is a system of nonlinear equations. What I like to do to start off these problems is to just get an idea of the picture, and with the picture it gives me an idea of how many solutions I might have. So when I look at this first equation, I notice that it's the equation of a circle. It follows that pattern of having x squared and y squared with a plus and equals a constant. The second equation is going to be a quadratic, although it is not a quadratic that we've studied in this class very much, because the squared is on the y coordinate instead of the x coordinate. And because of that, that quadratic has a parabola that faces left or right rather than up or down. So when I draw the picture of a circle and a parabola, I'm going to draw the parabola sideways. So when we draw the circle in this way, we're looking for the intersection points, and those intersection points would be the solutions. So if the circle and the parabola look something like this, we're going to get 4 solutions to the system. But this is not the only way to draw a circle and a parabola. You could have the vertex of the parabola just touching the edge of the circle. In that case, this would be 1 point and 2 points over here, so we would have a total of 3 intersection points, 3 solutions. Another possibility would be having the vertex being somewhere inside the circle. In this case, you would only have 2 solutions, and then you could also have the vertex just touching the circle, the edge of the circle. That would be 1 solution. And then finally, they could be totally separate, and you would have no solution in that case. So looking at these pictures, we can have as many as 4 solutions, all the way down to no solution. Then as I'm looking at this system, I'm trying to decide whether I want to use the method of substitution or elimination. I previously did this example with substitution, so I'm going to try it with elimination instead. So with the elimination method, you want to rearrange your terms so that you have the like terms lined up, most importantly, the equal sign lined up. So I'm going to rearrange by putting this y squared in the front. Now I'm not changing what side of the equation that y squared is on, so it's not going to change signs. So my new system is y squared plus x squared equals 16. And my second equation I'm just going to leave the same. And for the elimination method, we are going to eliminate the y variable because the y's have like terms. We're not going to be able to eliminate the x's because one has a squared, the other one is raised to the first power. Those are not like terms. They can't be combined. They can't be eliminated. So I need to make it so that those y squareds eliminate. They already have the same coefficient. I just need them to have opposite signs. So I'm going to multiply this second equation by -1. And now the system would look like this. The first equation is unchanged. Y squared plus x squared equals 16. The second equation becomes negative y squared plus 2x equals -16. And now we're going to use that elimination method. We're going to add the equations together. The y squareds cancel. The x's are going to combine. Excuse me, they don't combine together because they're not like terms. We'll just write them down. So it's x squared plus 2x. And 16 minus 16 is 0. So this gives me a quadratic equation to solve. I can solve it by factoring. I can factor out an x. That leaves me with x plus 2 equals 0. Set each factor equal to 0 using that zero product property. So I have x equals 0, and here if I subtract 2 on both sides, I get x equals negative 2. So this gives me part of the ordered pair solutions. I've got the x part, the 0 and the negative 2, and now I want to find the y part. So I can use any of the equations with two variables. Let's use this one here, the y squared minus 2x equals 16. For x equals 0, that would give y squared minus 2 times 0 equals 16. So y squared equals 16. And to solve, we'll square root both sides. That gives y equals plus or minus 4. So I started with one x value and it led to two y values. So that means I have two ordered pairs, 0, 4 and 0, negative 4. I want to do the same thing again, but with x equal to negative 2. That would give y squared equals, sorry, that's not an equals, that's a minus 2 times negative 2 equals 16. Y squared plus 4, negative times negative is a positive. I'll isolate the y by subtracting 4 on both sides. That's y squared equals 12. I'm going to solve for y by square rooting both sides. And that gives y equals plus or minus. We can write 12 as 4 times 3. Square root of 4 is 2. The 3 stays inside the radical. So once again, we started with one x value, but that led to two y values. So we have two more ordered pairs. That's negative 2 and 2 square root of 3. Negative 2 and negative 2 square root of 3. So for this example, we ended up with 4 solutions to the system of nonlinear equations. And those 4 solutions are 0, 4, 0, negative 4, negative 2 and 2 square root of 3, and negative 2 and negative 2 square root of 3. For this question, we want to use the graph of y equals 2 to the x and transformations to sketch the exponential function f of x equals negative 2 to the x minus 5. We want to determine the domain and range, determine the y-intercept, and find the equation of the horizontal asymptote. So we're going to start off by making sure that we know what the graph of y equals 2 to the x looks like. So we can do that with a quick chart. And we're going to substitute in negative 1, 0, and 1. So when we substitute into y equals 2 to the x, that would give 2 to the first, 2 to the 0, and 2 to the negative 1. 2 to the first is 2, 2 to the 0 is 1, and 2 to the negative 1 is 1/2. That's the reciprocal of the base. So we've graphed a few of these before, and we know that we'll take these 3 points, negative 1 and 1/2, 0, 1, and 1, 2, and we'll be able to connect these 3 points. On the right-hand side, the y's begin to get so large and it goes to infinity. And on the left-hand side, the y's continue to get smaller and smaller. And what we know about this is that there is a horizontal asymptote right on top of the x-axis. We have a horizontal asymptote at y equals 0. So that's what the original function looks like. Now we want to take that information and use it to help us graph this function right here, this transformed function. That's f of x equals -2 to the x minus 5. Now we have two transformations going on here. We've got this negative and the minus 5. The negative is going to be a reflection over the x-axis. That's a vertical reflection. And then the minus 5 is going to be a shift of the graph. This is going to be a horizontal shift moving to the right 5 units. But one of the things that we want to know is what happens to these ordered pairs that we got up here. How are those moved? So we'll take them one at a time. Let's start with a nice one that doesn't have fractions. So let's start with 1, 2. So the reflection over the x-axis is a vertical reflection, meaning that it's going to affect the y. And so what's going to happen is that ordered pair will transform to having the y-coordinate be the opposite of what it was. So it was above the x-axis at 2. When we reflect it, it's below the x-axis, becoming -2. Now the other transformation, I probably should have reversed these colors. So that one be green and this one be purple. So this shift to the right is going to affect the x because it's a horizontal shift. So moving to the right is going to affect that x value. So moving to the right is going to add 5 to that x value, so it becomes a 6. So we're going to do that same pattern with these other ordered pairs as well. So our other ordered pair was 0, 1. And with our 2 transformation, the y will be the opposite because of the reflection. And the x gets shifted to the right 5, so we add 5 to it. So that gives us with 5 and -1. Then for the last ordered pair, that was a -1 and 1/2. Once again, we're going to put a negative on the y, and we're going to add 5 to the x to take care of those 2 transformations. So adding 5 would make this x-coordinate 4, and then we get -1/2. So that's what happens to those specific points. Let's take a look at them. We've got 6, -2, 5, -1, and 4.5. Now, we started off with a horizontal asymptote right on top of the x-axis, and we will still have a horizontal asymptote right on top of the x-axis. The 2 transformations that we have here didn't affect that asymptote. A reflection doesn't change something that's on top of the x-axis, and a shift right or left doesn't affect what's right on top of the x-axis. Now, if we had done a vertical shift, that would change where the horizontal asymptote is. So this function has a horizontal asymptote at y equals 0. That's going to help us draw this left portion of the graph. We're going to approach that asymptote, getting closer and closer. On the right-hand side, we're going to go down to -infinity instead of +infinity because of that reflection. So we have now found the horizontal asymptote, but we have a few other things we need to find. We need to know the domain and range. Now the domain is going to be all real numbers. Every exponential function has a domain of all real numbers. Our range You can see based on our picture here that all of the y values are below the x-axis. So that means our range is going to start at negative infinity and go all the way up to the x-axis at 0. And notice I've used parentheses here because our asymptote shows that we're never going to reach the x-axis. We just keep getting closer and closer to it. The final thing that we need to know here is our y-intercept, and we're going to calculate that by hand. We find a y-intercept by letting x equal 0. In our function, that's substituting a 0 in for x, we get negative 2, and substitute a 0 in, negative 2 to the 0 minus 5, that's negative 2 to the negative 5. That's the same thing as negative 1 over 2 to the 5th power, and I believe that's 32. Let's double check. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So negative 1 over 32. And you can see by our picture here that that y-intercept would be very, very close to 0. So we've got a pretty accurate picture there. On this question, we want to use the graph of a basic function and a combination of transformations to sketch the function. So this function is g of x equals negative 1/5 absolute value of x minus 1 minus 6. So we want to start off by recognizing what basic function we have. And these absolute value bars are our clue that our basic function is y equals absolute value of x. We can sketch the graph of this with a few ordered pairs, negative 1, 0, and 1. Absolute value of negative 1 is 1. Absolute value of 0 is 0. And absolute value of 1 is 1. So this is one we work with a lot, so you're probably familiar that this graph takes on the shape of a V. We have 0, 0, 1, 1, and negative 1, 1. And we get straight lines that come to a point creating that V. So this is our starting graph, and we want to work through what transformations we have. So our function, g of x, equals negative 1/5 absolute value of x minus 1 minus 6 has 4 different transformations in this example. So let me try to distinguish each one of them with a different color here. So we have this negative, we have the 1/5, we have a minus 1, and let's get a blue, we have a minus 6. I forgot to write the minus 1 here. So you want to identify what the transformations are. To identify them, there are some memorizing that you have to do. So you have to memorize that multiplying by a negative is a reflection. You have to memorize that multiplying by a number is a stretch or compression. Subtracting and adding are both shifts. So these last two are going to be shifts. But this is still not enough information to get the graph. We have to know what type of reflection, what type of shift, what type of stretch or compression. So let's narrow down a little bit. This negative in red is on the outside of the absolute value, meaning that it is a vertical reflection. And a vertical reflection is going to reflect over the x-axis. So our final picture, because of that reflection, I should draw that in red to match my colors here, that final graph is, instead of being a V, will be an upside down V because of the reflection. So then with this stretch or compression, this 1/5 is also on the outside, so it's vertical. And then the fact that we're multiplying by a small number in between 0 and 1 means that this is going to be a compression. So we narrowed down that it is not a stretch, it's a compression because that number is small in between 0 and 1. With the shift, this first one, the -1, that's on the inside. Because it's on the inside, it's going to be horizontal. And horizontal is either going to be left or right. This is a minus, so it's going to be to the right. Then we have the -6. The -6 is outside of the absolute value. And so that is going to be a vertical shift. It's minus, so it's going to shift down. So there's lots of different ways that I could go about drawing this graph. I'm going to start with our basic graph, which I've already graphed in black. So this is what our starting graph looks like. And then I'm going to go in order. I'm going to start on the inside of the absolute value, and I'm going to show you with just this one transformation what the graph would look like. So if I shift all of these points to the right one, this is the picture that I would get. Still that V-shaped graph, but shifted to the right one. So that graph you see in green there is the graph of y equals absolute value x minus 1. So the next transformation I'll do is the reflection. With the reflection, we've already seen what's going to happen there. Our V is going to turn upside down. And now I'll take a look at the compression. So the vertical compression. Now the vertical compression means that, think about, since it's vertical, holding on the top and the bottom, you're going to flatten it out. You're compressing the graph together and it will flatten out. So instead of this going from 1 to 1 unit away, it's going to go by 1/5. So it will go flatten out like this. I think I went too far. But it's going to flatten out that V a little bit. Now, if you want to be more specific here, you could take that y value and multiply it by 1/5. So we had a y value of -1, it becomes -1/5. So then finally is going to be the vertical shift up. Let me get that color right, the blue. So if we go up 6, we'll be here, and remember it's going to be really, really flat because of the compression. So I didn't label all these properly. Let me label them. So this one in blue is y equals -1/5 absolute value x minus 1 minus 6. That graph in red has y equals, that's got the reflection and the shift to the right. And then the one in purple has the reflection, the shift to the right, as well as the compression. I'm going to pause here and see what else we need to address. Okay, so I'm coming back here because I made a mistake in this last transformation. This is supposed to be a shift down and I drew it as a shift up. So let's see if I can correct that mistake. So let's get rid of this graph in blue. And with the shift down instead, we would go 1, 2, 3, 4, 5, 6 down, and it would be very flat. So that is y equals negative 1/5 absolute value of x minus 1 minus 6. And that would be that graph in blue, that's the final graph that you want to use for the graph of our transformed function. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. So with this relating the bases method, we're writing it in this way so that we can apply the one-to-one property. And the one-to-one property says that when the bases are the same like this, the exponents must be equal to each other. So it allows us to simplify that equation into something that we're more familiar with. So this question has 1 over the 5th root of 216 equals 6 to the x. Now I have a base of 6 on the right-hand side, and on the left-hand side I have 216, which I believe is 6 to the 3rd power. So let me just double check on that. Yes, 6 to the 3rd power is 216. So it looks like I'm going to be able to write the base is the same on both sides with a base of 6. I have 1 over the 5th root, and I'm going to change that 216 to 6 to the 3rd. And one of the properties of radicals is that you can write them as powers. So I can write this 5th root as a 1/5 power. So this is the same thing as 1 over 6 to the 3/5 equals 6 to the x. Now one more property of exponents is with negative exponents. This exponential expression is in the denominator. I can bring it to the numerator by using a negative exponent. So this is 6 to the negative 3/5 equals 6 to the x. And now I've written this with the base being the same on both sides, so I can apply that one-to-one property and say that the exponent on the left has to equal the exponent on the right. And since we have x equals negative 3/5, we've solved our exponential equation. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. So we're going to use this method in order to simplify. Whenever we have our equation written in this form, we can use the one-to-one property of exponents to write this as u equals v. Once the bases are the same, the exponents must be equal to each other. So you can see in our example, we have e to the x squared equals e to the 35th over e to the x squared. All of these expressions have a base of e, so we're going to be able to write both sides of the equation with a base e. So on this one, we need to really refine our exponential properties. And the first thing I'm going to simplify is this portion right here. We're going to use a property of exponents called the power rule. In the power rule, it deals with this situation when you have an exponential expression like b to the m, and then that is raised to another power. So sometimes I call it power to a power. It's not totally accurate, It's an exponential expression to a power. And what we do to simplify is to multiply those powers together. So in our example, we have e to the x squared. We'll multiply those exponents together to get e to the 2x. So then we're going to simplify this whole right-hand side using another property of exponents called the quotient rule for exponents. And with the quotient rule, we have b to the m over b to the n. So here we're dividing, and our expressions that we're dividing have the same base. With that quotient rule, we subtract the exponents. So we have b to the m minus n. That's exactly what we have in my blue circle there, e to the 35th divided by e to the 2x. We're dividing expressions that have the same base. So we're going to subtract those exponents. So on the right-hand side, that's going to give me e to the 35 minus 2x, and on the left we have e to the x squared. So now we're at the point where we can use this property, this one-to-one property. We have made the bases the same on both sides, so those exponents must be equal to each other. We get x squared is equal to 35 minus 2x. This is a quadratic equation. We'll move all the terms to the same side. That's x squared plus 2x minus 35 equals 0. We're going to factor. We have x and x, 7 and 5, a plus on the 7, minus on the 5, and we're going to set each one of those factors equal to 0 using the zero product property. That gives x equals negative 7 and x equals 5. So we have solutions to this exponential equation of being negative 7 and positive 5. Thank you for checking out my videos. Have a great day.